Hey everyone, let's jump right into today's explainer. We've got an absolutely epic medical topic lined up for you. We're going to look at a completely devastating type of bone break, not just as a typical injury, but as a formidable monster that has to be conquered. We're talking about the subtrochanteric femur fracture. Now, this isn't your standard broken bone, no. This is a high-stakes surgical battlefield where the human body's most powerful forces are actively working against the cure. Okay, let's dive into this. How exactly does a surgeon defeat a fracture that actively fights back? You see, the subtrochanteric region of the femur, which is right below the hip joint, endures some of the absolute highest tensile and compressive mechanical forces in the entire human body. So when a break happens here, the dramatic tension immediately sets in. The orthopedic surgeon is basically stepping into a highly hostile environment where the body's own biomechanics are weaponized against the repair. And here is our antagonist. I mean, it looks less like a simple break and way more like a multi-headed beast pulling in a dozen different directions. Notice the really gruesome varus, that's the outward bowing, and the flexion, or bending forward deformities. The bone isn't just snapped in half, it's aggressively ripped out of alignment and held there. If a surgeon tries to just push this back together, the monster's gonna fight back, and fight back hard. So why does it look so chaotic? Well, it's because of the antagonist's relentless minions, the leg's most powerful muscles. Look at how they divide and conquer here. The abductors pull the top piece outwards into that varus deformity, the external rotators twist it, then you have the iliopsoas muscle aggressively pulling that proximal fragment forward into flexion. Meanwhile, the adductors grab the lower fragment and just yank it inwards, causing medialization. All these muscles are constantly firing, right? They're actively fighting the surgeon's attempt to restore order. Section 1. Choosing the ultimate weapon. Why older tools failed and IMN triumphs. To fight a monster like this, brute force just isn't going to cut it. Our hero needs to visit the armory and select the perfect technological weapon. In the past, surgeons wielded older weapons, like the screw and side plate construct that you see failing so dramatically here. It's really a striking image of defeat. These older tools fell out of favor because the deforming forces we just talked about were literally too strong. They led to incredibly high rates of hardware cutout, loss of reduction, and ultimately a need for a second surgery. The monster essentially won those battles. So, if the old tech failed, what is the ultimate weapon? Well, the answer is intramedullary nailing, or IMN for short. Instead of bolting a plate to the side of the bone, the surgeon drives a solid titanium nail directly down the hollow center of the femur. Because of its closed-section design, an IMN actually possesses a bending stiffness that's super similar to an intact femur. It spans the entire length of the bone, allowing for this incredibly efficient shared load transfer. Most importantly, it fiercely resists that mighty adductor pull that's constantly trying to collapse the leg. Section 2. The critical starting point. Precision is survival on the surgical battlefield. But here's the catch. Having the ultimate weapon means absolutely nothing if you don't know exactly where to strike. Precision is survival here. For years, surgeons used a starting point called the piriformis fossa. It offered a straight shot down the femur, but there was a massive problem. The entry window was incredibly tiny. If the surgeon was off by even a millimeter, the insane pressure of inserting the nail could cause the top of the femur to literally burst open. Because of this iatrogenic bursting, meaning a break caused by the procedure itself, the battlefield strategy shifted. Today, surgeons aim for the greater trochanter. It's a much more reliable subcutaneous entry point that drastically reduces the risk of shattering the bone. Now, what's really interesting about this slide is the sheer tactical brilliance required to use this trochanteric entry point. Because the trochanter isn't a perfectly straight line down the bone, pushing the nail straight in could accidentally crush the fracture into more pieces. To outsmart this, the surgeon performs a highly specific maneuver. They rotate the nail 90 degrees so its natural curve faces inward, they advance it carefully across the jagged fracture site, and then they slowly derotate it back into position. Honestly, it's kind of like picking a high-stakes biomechanical lock. And that brings us to this vital surgical secret, slight medialization. This is absolutely crucial. If you enter too far to the side, the bone collapses into that monstrous varus deformity we talked about earlier. But by deliberately cheating the starting point just slightly medial, towards the inside, the surgeon induces a tiny bit of valgus, or slightly inward, alignment. This brilliantly counteracts those massive muscle forces, protects the vital abductor tendons, and basically guarantees a straight leg. All right, Section 3, an arsenal of tactics, outsmarting the deforming forces. Even with the perfect starting point, actually getting that nail down the bone isn't a walk in the park. Pulling on the leg with standard traction on the operating table rarely overcomes those monstrous muscles. The surgeon has to deploy a specialized arsenal of combat tactics. The first line of defense? Physical wrestling. Surgeons will literally drill thick metal shank pins right into the broken pieces, attach T-handles to them, and use them as percutaneous joysticks. I mean, imagine trying to realign a broken concrete pillar while heavy steel cables are actively pulling it apart. That's exactly what the surgeon is doing here, physically wrestling the bone into place just to let the guide wire pass through. But hey, sometimes joysticks just aren't enough. When the bone is stubborn and refusing to straighten out, they bring in precision tools. The surgeon makes a tiny incision and slides a finger reduction tool straight down the canal. This metal finger slips past the fracture site, literally physically pushes the jagged fragment out of its varus deformity, and holds the monster at bay just long enough to slide the vital guide wire perfectly down the center. And this brilliantly illustrates one of my absolute favorite tactics, the blocking screw. The surgeon drives the screw right into the concavity of the deformity before the nail even goes in. You know how the broken bone naturally wants to cave inwards? Well, this screw acts like a concrete barricade to stop it. When the nail is driven down, it hits the screw and is forced right down the correct path, locking the bone straight. It's quite literally deploying reinforcements to hold the line. Finally, for the absolute most stubborn beasts out there, there is the clamp-assisted reduction. The surgeon makes a small open incision, goes directly to the fracture, and clamps the bone fragments incredibly tightly together. It's the definitive tactic. Once that clamp is locked, the monster is fully subdued, ensuring total anatomic victory and allowing the IMN to be placed flawlessly. Section 4. Claiming surgical victory and restoring order to the proximal femur. Which brings us to the aftermath of this incredible battle. The nail is in, the forces are balanced, and order is finally restored. But listen, the tools alone didn't win this fight. As our source authors point out, and I'll quote, "Technique is primary." An intramedullary nail is, at the end of the day, just a piece of metal. It is the surgeon's flawless technique, understanding the anatomy, manipulating the starting point, and commanding those reduction tools that is the true hero here. So why does mastering all of this matter? What's the ultimate reward for the patient? Because the surgeon used these precise, minimally invasive tactics to outsmart the deforming forces, the patient benefits immensely. The leg's mechanical axis is perfectly restored, there's way less tissue damage and less blood loss. And incredibly, because the IMN shares the load so well, a patient who literally just suffered a catastrophic monster of a fracture might actually be allowed to stand up and bear weight on that leg immediately after surgery. That is just staggering. It leaves us with a truly fascinating thought to end our explainer today. If we can engineer titanium nails, percutaneous joysticks, and strategic blocking screws to outsmart the human body's absolute strongest muscles today, what incredible medical marvels will surgeons command tomorrow? The biomechanics of our bodies are awe-inspiring, for sure, but the sheer ingenuity of modern medicine to fix them might just be even more impressive. Thanks for joining me on this explainer, and keep exploring.